Alright, we're going to talk about the action potential, and before we can talk about the action potential, we are going to talk about a resting potential or a polarized cell. So what you have in your worksheet here is you have the extracellular fluid on the outside. The lines are representing the membrane, if you will, of the axon of the neuron, and then you have your intracellular fluid, the things that we would find inside the cell. So one of the things that we talked about in class is we have some leak channels on the cell membrane, and they're peppered all the way around, but we did talk about the fact that we have roughly 2 potassium leak channels to that of 1 sodium leak channel. So with that being said, potassium is definitely going to be more permeable because it is allowing more potassium to leak out, if you will. And we know that potassium is going to move this way, and sodium will move towards the intracellular fluid. So with that being said, we really refer to the potassium leak channels as being more permeable. Now, if we had more sodium leak channels, then the sodium would be more permeable. Now, as far as our environments go, on the inside of the cell, the intracellular fluid, we know that we're going to find large negative proteins, and these do not ever leave the inside of the cell. They stay stationary the whole entire time. We will also find lots of potassium on the inside of the cell, as you can see here, and we will also find a little bit of sodium. But our main ion, if you will, on in the intracellular fluid is that of potassium. As far as the extracellular fluid, our main ion on the outside here would be sodium. We also find about equal amounts of chloride to those sodium. And we do find some potassium. And again, the reason we're finding a little bit of sodium on the inside and a little bit of potassium on the outside is because of these leak channels, which, as the name suggests, they leak, they're always open. So when we look at the charge difference between the outside and the inside of the cell, we would find normally a more negative environment on the inside compared to the outside, which is a more positive environment. And like we talked about in class, if I were to stick a probe in there, it would measure out about negative 70 millivolts. Now, the reason why it's more negative on the inside is because we're losing these potassium ions through the permeability of the leak channels. And why is it more positive on the outside is because we typically will see these potassium ions on the outside, because the chloride and the sodium, they would equal each other out, if you will, and we're left with more of the positive potassium ions on the outside. Now, this would continue, potassium and sodium would continue to leak one way or the other, and ultimately they would stop when both sides were equal, and that's the law of diffusion. And so somehow we need to reset the ionic concentration difference, and that would be the role of the sodium-potassium pump that we see here. And one thing I think I kind of goofed up on a little bit was the ratio of sodium to potassium and how much of each were going in and out of the cell. And so the actual ratio is that we're pumping 3 sodium out and we're pumping 2 potassium back in. So this is the correct ratio in the direction of each of those ions that they need to go. Now remember, the sodium-potassium pump is an exchange process. It does require ATP for that. So this is our resting potential, or our polarized cell, basically saying that this cell is not being stimulated by anything, and in a resting state you would see this particular setup. Now, when the cell is stimulated by a graded potential and eventually becomes an action potential, the action potential is occurring on the axon. So when an action potential occurs, we have 2 phases to that: depolarization and repolarization. So our first phase is depolarization. Let me just make sure I look at the camera and adjust this. Okay, so there's our next phase, depolarization. So we would like to start with the inside of the cell, and essentially you're going to copy exactly what we had in the resting state. So lots of potassium here. a little bit of sodium, and then our negative proteins that we would see here. Now in this case we're not concerned about the leak channels anymore, because although they're still active and leaking, they don't play a major role in the depolarization state. The major role that's going to play in the depolarization state would be these voltage gated channels, and so we have two of them. I am color coordinating them according to the ions that they belong to. So there's your sodium and there's your potassium voltage gated channel. Now these voltage gated channels are only going to open up when they've been stimulated, and when we talk about stimulation we're talking about a graded potential acting on the axon to bring about an action potential. And we talk about being stimulated, we're talking about changing the environment of the inside of the cell to become more positive, as we will see here. On the outside of the cell we have all of our sodium, we have our chloride, and like before we have some potassium. So when we get a stimulus, if you will, represented by this line, it's going to allow the sodium voltage gated channel to open up. Now in class I said that the potassium voltage gated channel will for the most part stay closed, but during this depolarization the sodium voltage gated channel will open, and ultimately the sodium will rush in. And when I say rush in, we have a lot coming in, and the reason for that is because we have so much sodium out here where we have very little in here, and so it's a natural response for it to rush in. And remember that it will stop rushing in, if you will, when both sides are equal. So if I put a bunch of sodium in here, that's because the sodium has rushed in and because the voltage gated channels have opened. Now because the sodium has rushed in, we have a lot more positively charged ions in here compared to what we did have. And if we wanted to eliminate some of these sodium out here that have essentially rushed in, that would ultimately leave us with a more negative balance on the outside. So we'd see more of a negative balance on the outside compared to the inside with the positive. And like we said before, when you measure the voltage, you're always measuring on the inside of the cell. We don't really care so much about the voltage on the outside in comparison to the inside. And if we did that, we're looking at about a positive 30 millivolts. And so we've seen a change in the potential of this particular membrane, if you will, and that's what an action potential is. And ultimately, this is happening throughout the axon, and like we said, it's happening in a graded response, or sections, if you will, versus the whole entire axon going through this process all at once. Are the leak channels still open? Yes. Is the sodium-potassium pump still working? Yes. Ultimately, they are not playing a huge role in what we want to recover here. So immediately after a section of the axon goes through this phase of depolarization, then what we need to do is look at our next phase, which immediately happens afterwards, which is repolarization. So if you flip your page over, you'll see repolarized state. Now, we'll put in our sodium voltage gated channel. We'll put in our potassium voltage gated channel. And we are also, in this particular phase, we're going to put that sodium potassium pump in, and we'll come back to that in just a minute. As far as where we left off, we had a lot of potassium inside the cell after depolarization. And we also had all that sodium that had rushed in, so we'll put those in here as well. We still have our negative proteins, which never do leave the inside of the cell. On the outside, we still have some sodium, not as many because they rushed in. We still have lots of chloride that never moved in this particular example. and we still had some potassium, because remember, the leak channels are open, so you're always going to have a little potassium on the outside no matter what. Now in repolarization, the sodium voltage gated channel closes, and that closes right after depolarization. So once it closes, and the depolarization phase is done, we get the potassium voltage gated channel to open up. Now during this phase, potassium now, there's more potassium on the inside of the cell than we have on the outside, so ultimately the potassium is going to rush out because there's a gradient difference, and that's again diffusion. When would it stop? Just like it was before, when both sides would be equal. So in this example, we can put a whole bunch of potassium now on the outside of the cell because they rush through. And if you want to, you can cross out a few of these potassium molecules to show that they actually did move out into the extracellular space. Now, because essentially what's happened in this whole entire situation is that our ions have flipped spots. We now see more sodium on the inside of the cell, and we see more potassium on the outside. So ultimately, our charge is going back to where we started, with a positive on the outside in comparison to the inside with being more negative. Now what happens during this phase, though, is if I were to put a probe in here, it would measure to be about a negative 90 millivolts. And the reason for that is because we have a little extra potassium that goes out than the amount of sodium that came in. And so with that being said, because we had a little extra dip in the millivolts, this is called hyperpolarization. Hyperpolarization. So when there was two questions I continued to ask to make sure you were keeping track is, in each of these phases, what was the ionic concentration difference? And what I'm trying to tell you is, or what I want you to know is, what would you see on the outside of the cell in comparison to the inside as far as the ions go, and the makeup of that? And then the other thing I asked you to keep track of was, what was the charge difference from the inside to the outside of the cell? So in this example, our charge is back to where we want it, where we initially started in a resting cell, but our ions have been flipped. So this is where the sodium-potassium pump comes into play, and ultimately is going to exchange potassium and sodium from one side to the other, and that truly resets the ionic concentration difference, but it does not do anything to the charge. So again, it will move 3 sodium out, and it will move 2 potassium in. And again, contrary to the confusion that I made for myself in class, this would be the correct exchange ratio of sodium to potassium. So this is a kind of a condensed, very quick version of resting, depolarization, repolarization. And understand that graded potential goes through the same steps here, but remember, a graded potential happens on the dendrites of the cell body, and it may not have enough strength to make it to the axon. And if it does have enough strength to make it to the axon, on the axon is where we're seeing, or how we're referring to it as being the action potential. Now an action potential is going to occur all the way to the end of the axon. It will always have enough strength to do so, and so we don't have to worry about that. So just remember, in class I said a graded potential is like if you had a row of dominoes and you just lightly hit the dominoes, it may or may not, knock them all down. Whereas if you hit it really hard, it would knock them all down, which would better represent an action potential. So with the last two questions here, it says, what is the role of sodium-potassium pump, and what is the ratio of ions in and out? And so we kind of answered this already, but its role is to exchange the ions, and it's an active form of transport. And the ratio, again, would be 3 sodium out and 2 potassium in. The last question, which we have already answered as well, is what is the difference between a graded potential and an action potential, and where are each of these taking place in the neurons? So we just covered that a minute ago, so you can fill in those blanks as well if you need. So this is kind of a real quick recap of what we went over. Hopefully you guys can use it, go back and rework it. I think more importantly, you need to be an active learner. Keep drawing this out instead of staring at it. It will help you ultimately on your exam. Please don't forget about the other handout that I gave you on the second packet we weren't able to go through. Those questions will be on the exam in some way, shape, or form. Please look in your book for those answers would be the best thing versus trying to read them off the PowerPoint, as the notes there would have been explained to you in class. Anyway, have a wonderful break, and we will see you back next week. Take care.